the set of integers is denoted by the symbol Z. It's a Z written with a double line here. Let A be an integer, so it's written as A belongs to Z, so this symbol is belongs to. Let D be a non-zero integer, and we say that D divides A if there exists an integer C such that A is equal to DC. So let A, B be integers and N a non-zero integer. We say A is congruent to B modulo N if N divides A minus B. And these have these properties. Right? If A is congruent to B modulo then AC is congruent to BC modulo N, where C is an integer, and A to the power K is congruent to B to the power K modulo N, where K is a positive integer, H2 for positive integers. It's useful to know this factorization. So A minus B divides A to the power K minus B to the power K. If we put A is equal to B in AK minus BK, we get AK minus AK equal to 0. So by the factor theorem, A minus B divides AK minus BK, and also this factorization is, we can just work it out right now. A minus B, so we need to multiply it by A to the power K minus 1, so we get AK, and then minus B A to the power K minus 1. We don't want that, so we'll add B A K minus 2. So these terms will get cancelled, and the second one would be, so the powers of B will keep increasing and powers of A will keep decreasing till B to the power K minus 1. So in congruence notation, it can be written as A to the power K is congruent to B to the power K mod N. And over here we don't divide by 0, so D is a non-zero integer, and A can be 0 because a 0 can be divided by any number, so A can be 0, so A is an integer. Similarly, this A plus C is congruent to B plus C mod N. This can be written as A plus C minus B plus C is equal to A minus B, and N divides this expression, so N divides this entire thing, so this comes from like this. So now we'll talk about decimal representation of an integer, and also a few divisibility tests. We already know divisibility by 2, 4, 5, 3, 9, 10, 11. Yeah. So suppose N is written as AK minus 1, A0, where all of these are belongs to 0 to 9. And AK is not 0, let's say. So the meaning of this is this: N is equals to A0 plus A1 into 10 plus A2 into 10 square, AK into 10K. if we subtract the sum of these digits a naught, a plus a1 to ak from this, a naught gets cancelled. And each of these factors 10 to the power k minus 1 is divisible by 9 as using this, putting b is equal to 1 and a is 10, so 10 to the power k minus 1 is divisible by 10 minus 1, 9. So this is, so 9 divides each of these terms, so 9 divides the sum of them. So 9 divides n minus this thing, so this is written this way. And since 3 divides 9, the same from the same series of arguments, it follows that 3 divides n. And for divisibility by 2, we just have to look at the units digit, because n minus a naught is this, and each of them, 2 divides 10, 2 divides 100, 2 divides 10 to the power k, so 2 divides the entire thing. And if we want to look at divisibility by 4, so we have to subtract a naught and 10a1. In that case, this is cancelled, and 4 divides 10 square, 10k, 10 cube, 10k, so 4 divides this entire expression. Similarly, divisibility by 5, if we look at n minus a naught, 5 divides this expression. a1 10, a2 10 square. 5 divides each of these expressions, so 5 divides some of these expressions. So we can also work out that proof. Suppose n divides a and n divides b. So a can be written as nk1 for some integer k1, and b can be written as nk2 for some integer k2. A plus b. So n divides a plus b. The next is divisibility by 11. So for the divisibility test, divisibility by 11, a test for that, let us look at this expression. This was n, a0 plus 10, a1 plus 100, a2, and minus times the unit digit plus the digit in the 10th place, and minus the digit in the 100th place. Yes. So this becomes, for odd powers of k, it becomes 10k plus 1, and for even powers of k, it becomes 10k minus 1. For example, 10a1 minus 10a1 plus a1, so this is 10 plus 1, and then 1000 is 10 cube, 10 cube a3 plus a3 is 10k plus 1. So k is equal to 3 there. And 11 divides 10k plus 1. If k is odd, we can look at this here. X plus y is a factor of x to the power n plus y to the power n. Why? Because if we put x is equal to minus y or y is equal to minus x in this one, we get x power n plus minus x to the power n, which is equal to 0 if and only if n is odd. So putting y equal to 1, 11 divides 10k plus 1 if k is odd. 10k minus 1, this factorization can be used. Putting y as 1, this will become 9. And this expression n minus 1 is odd and y is equals to 1. So it is 10 to the power n minus 1 plus 10 to the power n minus 2 plus 1, something like this. And because n minus 1 is odd, so we'll have n minus 1 is odd, so we'll have even number of terms here which can be paired. The consecutive terms can be paired. So over here 10 plus 1 is 11. 10 cube plus 10 square can be written as 10 square 10 plus 1, and then so there's 11 in each of these pairs. So this entire thing is divisible by 11. So 11 divides 10 to the power k minus 1 if k is even. So if 11 divides 11 divides this expression, and if 11 were to divide this one, then 11 has to divide this, because if n divides a plus b and n divides a, and a plus b is equal to nk1, a is equal to nk2, b is equal to nk1 minus a implies n divided b. So similarly here, so the divisibility is so you have to look at the sum of the digits. If 9 divides the sum of the digits, then and 9 divides n minus this, which was shown here. So 9 divides n. And similarly for 3. And if 2 divides a naught, so a naught is an even digit. So 0, 2, 4, 6, 8. And in the case of 4, if 4 divides this and 4 divides n minus this, so 4 divides n. And similarly for 5, if 5 divides a naught, that is a naught is equal to 0 or 5, then 5 divides n.